Today we'll look at circuits with multiple, that is, two loops. The two circuit laws we use are Kirchoff's voltage law, which applies to loops, and Kirchoff's current law, which applies to nodes, that is, where two or more wires come together. Kirchoff's current law states that the sum of the currents entering a node is zero. The laws are named for Gustav Kirchoff, who was a 19th century German physicist. The circuit shown is a low-pass filter. That is, when the input generated by the signal generator is a low-frequency sine wave, it appears at the circuit output, taken as the voltage at node 3, at close to full amplitude. When the signal is a high-frequency sine wave, its amplitude is attenuated. The circuit has two loops that are labeled L1 and L2, as well as a loop around the perimeter of the circuit. Kirchoff's voltage law applies to all these loops. The nodes in the loop are labeled 0, 1, 2, and 3. By convention, node 0 is grounded. That is, it is held at 0 voltage, volt, after Alessandro Volta, an Italian physicist of the early 19th century. We're going to introduce some new notation. The notation V sub ij is used to denote the positive voltage between nodes I and J, and the notation I sub ij is used to denote positive current flowing from node I to node J. Now we can develop the model for this circuit. There's only one state variable, the capacitor voltage, and we need a differential equation for its rate of change. We start with the capacitor model, which is the rate of change of the capacitor voltage equals the capacitor current divided by C, and looking at the diagram, that is I20 divided by C, where I20 is the current from node 2 to node 0. However, I20 is not a state variable, so we need to find an expression for it that only involves state variables. So let's look at what's happening at node 2. The current into node 2 is denoted by I12 plus I02 plus I32, and it all sums to 0 by Kirchoff's current law. Also, the current out is I21 plus I20 plus I23, and that also equals 0 by Kirchoff's current law. Or we can say that the current in through I12 and I32 equals the current out through I20, and that's what we'll do. That's our second equation. Now let's look at I12. It is the negative of I21, and I21 is the current through R1 and is given by Vc minus Vs divided by R1. So I12 equals Vs minus Vc divided by R1, and that's our third equation. How about I32? I23 is Vc divided by R2, so I32 is minus Vc divided by R2, and that's our fourth equation. Substituting into the differential equation, we have the rate of change of the capacitor voltage equals I20 divided by C, which equals I12 plus I32 divided by C, which in turn equals Vs minus Vc divided by R1 minus Vc divided by R2, all divided by C, and that's the differential equation model that we will use. Using that differential equation, we can write the computational equation as shown. Do we want to do some hand calculations? We do. We'll program the signal generator to generate a unit impulse at t equals 1 second, and the circuit parameters are capacitance C equals 0.2 farads, R1 equals 0.2 ohms, and R2 equals 10 ohms. We'll set dt to 1,000th of a second to get high resolution for the impulse response. So everything is quiet in the circuit till t equals 1 second, when Vc equals 0 and Vs spikes to 1,000. Now we start calculating at 1.001. Vc at 1.001 equals Vc at 1.000 plus Vs at 1.000 minus Vc at 1.000 divided by R1 minus VC at 1.000 divided by R2, all divided by C times dt. And plugging in the numbers, we get VC at 1.001 equals 25. Then VC at 1.002 equals VC at 1.001 plus quantity VS at 1.001 minus VC at 1.001 divided by R1 minus VC at 1.001 divided by R2, that quantity divided by C times dt, and plugging in the numbers, we get 24.3625, and so on. Letting the computer do the rest of the calculations, we get the graph on the left. The other two graphs show the filter response for a sine wave at 3 Hz and a sine wave at 30 Hz. If you note the vertical scales on the graphs, you'll see that the amplitude of the 3 Hz wave is nearly full amplitude at 1 volt, while the amplitude of the 30 Hz wave is attenuated to 0.15. So the circuit is performing as a low-pass filter as advertised. Now we'll look at the circuit for a high-pass filter. There are two energy-storing components in the circuit, a capacitor and an inductor, so there will be two state variables, one for the capacitor voltage and one for the inductor current. From the inductor model, we have the rate of change of inductor current equals VL divided by L. And from the circuit model, we see that the inductor voltage is the voltage at node 2. Noting the capacitor polarity, the voltage at node 2 is Vs minus Vc, so the inductor voltage is Vs minus Vc, and we have a differential equation for the rate of change of the inductor current, namely, the rate of change of inductor current equals Vs minus Vc divided by L. From the capacitor model, the rate of change of capacitor voltage is the capacitor current divided by C, and the capacitor current is I12. So we need an expression for I12 in terms of state variables. Looking at node 2, the current in through I12 equals the current out through I20 and I23. I20 equals the inductor current, so that's a state variable. The voltage at node 2 is Vs minus Vc, so I23 is Vs minus Vc over R. So making these substitutions in the equation for the rate of change of capacitor voltage, we have the rate of change of capacitor voltage equals I12 divided by C, which equals the inductor current plus Vs minus Vc over R, all divided by C, and that's the differential equation model we need. From the differential equation model, we can write the computational equations as shown. This time we'll skip the hand calculations. The graphs show the filter response for a unit impulse, a sine wave at 1 Hz, and a sine wave at 50 Hz. Noting the vertical scales on the graph, the amplitude of the 1 Hz sine wave is 0.05, while the amplitude of the 50 Hz sine wave is very close to 1. So the circuit is performing as a high-pass filter as advertised. This is about as far as we will go analyzing circuits, but the methods we have used can be extended to more complex circuits, and there is a methodical approach for deriving the equations, which we've done in an ad hoc manner. The subject is pursued at greater length in the videos identified below, and links to the YouTube videos are in the class notes. In the next lesson, we will look briefly at models for transformers and transistors, but not attempt to analyze them. Then we'll take a brief look at SPICE, the industry standard circuit analysis tool. The assignment for this lesson is to duplicate the results in the video.